All right, so this is our second presentation on Chapter 11, Solutions and Their Properties. So we're continuing on with the colligative properties more individually and in more detail as we left off at the end of the last presentation. So here we're looking at vapor pressure lowering of solutions, where we talk about Raoult's law. So Raoult's law is the equation here that we'll use to calculate the new vapor pressure of a solution given the formation of some solvent with some solute in it and the additional parameters that go into that. So they talk here about a thermometer. They can measure the vapor pressure of a liquid, and you can see how when you add a non-volatile solute, the vapor pressure goes down. So if I have a non-volatile solute, so basically what they mean by this is a solid or a very or less volatile liquid added to a liquid, we will generally see the overall vapor pressure go down. So when we look at this vapor pressure, right, we'll want to take the partial pressure that would normally be the partial pressure of this solvent liquid times its mole fraction. So this is the mole fraction solvent to get the new partial pressure, the new vapor pressure of the solution here. So what they show is that if I take typically you can find the vapor pressure of the solvent as the vapor pressure of the liquid at a given temperature, right? So they say here that the vapor pressure of pure water at 25 degrees is 23.76 millimeters of mercury. Again, this isn't something you would need to memorize, but that's where this is coming from. I put that in for the vapor pressure of the solvent at this given temperature. Then, because it's made into a solution, I take the mole fraction of the solvent. So I take, here it's 15 moles solvent and 1 mole solute. So they say here a solution of 1 mole glucose in 15 moles of water. So I have to take, so this is where I need to use the mole fraction like we discussed in the previous lecture, but I have to put it in frame of the solvent. So I put the solvent amount on top, then the solute plus the solvent on the bottom. So basically it's like I'm applying a sort of percentage to the vapor pressure of the solvent, because for whatever percentage of this, it remains solvent. So it's kind of like, we could say maybe that like 98%, it's now 98% solvent instead of 100% solvent. And we're multiplying that by the vapor pressure of that solvent, and then that gets me the vapor pressure of the new solution. And then they calculate a change. So there's a vapor pressure lowering, right? Alternatively, the amount of vapor pressure lowering can be calculated directly by multiplying the mole fraction of the solute times the vapor pressure of the pure solvent. So here they show this calculates the change. So if you wanted to get the change, you can take the solute times the solvent, and that'll give you the change. Some students find this as an easier way of calculating, because remembering to do this as the solvent can sometimes be confusing. So they'll do the mole fraction solute times this and then do a subtraction. So you subtract this 1.49 from the 23.76 and you'll get 22.3. So this is an important note. Sometimes this is an easier way to get it especially if they're looking for the change. This is a direct way to calculate that, just a little bit easier. But the standard way, of course, is this first equation, and the one that's drawn here in the box is the standard Raoult's law. Now, a solution that follows Raoult's law is said to be Raoultian, so keep that in mind, or a form of ideal solution. And we'll talk about deviations from that a little bit too. Now, also keep in mind that if the solute breaks apart into particles, then you'll need to multiply the number of particles by the moles by the number of particles that are produced. So if we have something like NaCl, it breaks apart into 2 ions, we'll need to have both those ions in the fraction, or another way to write this is to put a 2 in front of the concentration of the NaCl, the moles of NaCl here. So you'll have to have 2 moles because of the units formed. So keep that in mind. When you have something that breaks apart into particles, you have to multiply the number of moles by the number of particles that produces, or just include each one here individually. So now we've increased this. So you'll see that we get more vapor pressure lowering here because we've got a bigger denominator down here, so this now goes down. So this will produce an even smaller number because of this increased number of particles. This is part of what makes Raoult's law colligative. It depends on the number of particles, but not their identity. It doesn't matter that this is sodium and this is chlorine. It just matters how many particles there are. And then we express that in moles, right? An ideal solution is Raoultian, okay, meaning that it follows Raoult's law. Raoultian is just another way of saying that a solution follows follows Raoult's law. And an ideal solution is a Raoultian solution, and we'll get into that a little more in detail because there's other properties of an ideal solution than just being Raoultian, but all ideal solutions are also going to be Raoultian. That is to say, they're going to follow this. Raoult's law works with dilute solutions. Dilute solutions tend to be the closest to Raoultian, and also where the solute and the solvent particles have very similar forces, right? If the intermolecular forces between the solute and the solvent are weaker than the forces between the solvent particles alone, and the solvent particles are less held tightly, and the vapor pressure then will be higher than Raoult's law predicts. Or conversely, if the interaction between the solute and the solvent is much more favorable than what would have been in the solvent by itself, then the vapor pressure can be lowered more than predicted, because the solute has a disproportionate impact on holding the solvent together. You'll see that, like in the equation, when we look at the math of how Raoult's law works, we're sort of assuming that it's just a number of particles that matters, that their identity doesn't matter, and this is sort of like a percentage applied onto the vapor pressure of the solvent, right, like we had mentioned before. That's an estimate if these parameters are not quite right. An ideal solution, the interaction between the solute and the solvent is similar to the solute in itself and the solvent in itself. If that's not a true assumption, then that solution will not follow Raoult's law. It will be said to deviate, and it'll either be vapor pressure will either be higher or lower, depending on whether the deviation is because the particles are more weakly attracted than they should be, or more strongly attracted than they should be. A stronger attraction lowers the vapor pressure more because it holds the solution together better. A weaker attraction means means more vapor pressure and a lower boiling point. The boiling points get elevated by adding this in here. So solutions of ionic substance in particular often have vapor pressure significantly lower than predicted because the ion dipole forces between the dissolved ions and the polar molecules are so strong. So ionic compounds can often cause deviations from Raoult's law and give a lower vapor pressure than predicted. This is accommodated by the Van 't Hoff factor. One way to understand what's going on in the solution is to think about this Van 't Hoff factor as being applied to the concentration of something that breaks up into ions. So we can say that this concentration here is, or this mole fraction here is the water moles times the Van 't Hoff factor, which is the number of ions it breaks up into, times the concentration of the solute, the moles of the solute, and then plus the moles of the water here. So when we think about this Van 't Hoff factor, this is how many ions actually get produced when something dissolves. And it's experimentally measured, right? Sodium chloride doesn't really give exactly 2, just because it breaks up into 2 particles. That'll be our estimate. If we don't know the real Van 't Hoff factor for a substance, right, we'll assume that it breaks apart into the number of ions that it would break apart into as an ionic compound. But we know that in reality there's some ion pairing and it's not perfectly ideal. So sometimes these ions kind of come back together and act like 1 unit in the solution instead of acting like truly 2 units. And that's accounted for by the fact that this is a 1.9 instead of a 2. So that's just something else to kind of keep in mind here, that the Van 't Hoff factor for a 0.05 molal sodium chloride solution is 1.9, so not quite 2, because it should give 2 moles of ions for every 1 mole of sodium chloride. So that's something that we should think about. 1.9 particles, 0.9 sodium chloride, right? Of course, then there'll be some undissociated sodium chloride that kind of floats around. Thus, sodium chloride is only 90% dissociated, and the amount of vapor pressure lowering is less than expected. So the vapor pressure is higher than you'd expect because we don't get perfectly that many ions. But it's a good approximation, right? If we use 2 for 1.9, we really wouldn't have too much of an issue. So keeping all of this in mind, right? They say here, what is the vapor pressure in millimeters of mercury for a solution made by dissolving 18.3 grams of sodium chloride in 500 grams of water at 70 degrees Celsius, assuming a Van Hoff factor of 1.9. So what they've done here is they've said, okay, so we're going to convert these grams to moles, right? And also get the moles of water so we can set up the mole fraction. So what they did is they took the 1.9 times the 0.313 to get this 0.59. You could almost think about this 0.59 down here in the denominator as I, the Van Hoff factor, times the moles of the total sodium chloride here. And that's why I'm saying that's another way to think about how you put the solute in here. It's not really, in this instance, in Raoult's law, it's not, they write it as this X solvent, but it's not really. It's really moles solvent over the number of moles of particles generated by the solute plus the moles solvent. Because the number of ions that the water produces on its own with self-ionization is not significant. But you can see that Van Hoff factor is 1.9, and then we can calculate what the vapor pressure actually is. And they say this is at 70 degrees Celsius, and that's fine. We don't have to change that. We just have to use that vapor pressure that we're provided. So a problem will give you a Van Hoff factor like this if you need to use one. Otherwise, if they don't give you a Van Hoff factor and they give you something like sodium chloride, you put in a Van Hoff factor of 2 because that's what it breaks up into. So if you were approximating this and they did not give you this 1.9, you'd assume this is a 2. You'd take your 0.313, multiply by 2, and then put that into your mole fraction. Keep in mind that this is not a true mole fraction anymore. Like if you were calculating a mole fraction, this is no longer a true mole fraction. When we have to break this up into ions, we've sort of modified this formula. And that's why I say sometimes I like to think that this is not really the case. This is not really X solvent. This is really moles solvent over the solute's number of ions plus moles solvent, like the way they break this down here. And it's not really a mole fraction anymore. It is a mole fraction as long as things don't ionize, but it's more of a mole fraction ion. It's not the way they teach you to calculate the mole fraction earlier on. So I'm really pointing this out to you because you will get incorrect answers if you don't review this problem and how this works. And like I said, if they did not give you this Van Hoff factor, you would use a 2 there. Okay? And if they didn't give you the vapor pressure of water and they didn't give you a temperature, you would go look up in an index or find out what the vapor pressure of water is at 25 degrees Celsius, and that's what you would use. So assume 25 degrees Celsius if they don't tell you. Use any vapor pressure a problem gives you. Use any Van Hoff factor a problem gives you. But if they don't give you those things, assume the number of ions get produced as it breaks apart, and assume that it's at 25 degrees Celsius, and that's what vapor pressure you need to use if you're not given a temperature. Here they give us another example. They say how many grams of sucrose must be added to water to lower the vapor pressure by 1.5 millimeters of mercury at 25 degrees Celsius. The vapor pressure is here, and the molar mass of sucrose is this. Now, here they don't give me a Van Hoff factor. Now, sucrose, and this will be true for anything that you encounter where you don't know what it is. If they don't tell you it's an ionic compound and you don't recognize this as an ionic compound, you assume the Van Hoff factor is 1, and you progress with a normal mole fraction. That's how you should approach these problems. So they give me the vapor pressure of water. Okay, so I have that. I got to put that into my Raoult's law. But now I got to get this X, or sometimes they call this a chi solvent here. How do I get that? Well, I'm going to need the moles of the water, so I got to convert this to moles. I got to convert this to moles, and they do that step here and get 17.8 moles. And then they got to convert the sucrose here to moles. They say how many grams of sucrose, but I don't know what that is. I've got to somehow convert that to moles, though, so maybe I can plug that in. I can say that the grams of sucrose are some X that I need to solve, and then I'm going to divide that grams by this number to get moles to plug it into my equation. So you could do that if you wanted to do a little more sophisticated algebra, or you could just work through the whole problem and solve for the number of moles, right? So we know this is total moles, so we know that we can figure this out from further review. So here they say, okay, we've got this vapor pressure lowering, we can solve this, right? we can solve this equation with this P solution, P solvent, to get this X. So we have the value of this X here as 0.937. And we got the moles of water. We can get this moles of sucrose from the remaining moles that are needed, and they calculate the total moles, which is what they do here in this step. What they do is they plug in the moles of water and then they solve for that. They subtract the water from that, and then they can convert that into grams. So you can do this in a number of different steps, but really what you're focusing on is rearranging this X solvent. And you can imagine this total moles is moles water plus the moles you don't need, and then that's the subtraction that they're doing down here. I like the way that the book presents this, but know that there's different ways you can kind of start from this equation and plug in each of the steps that you need and kind of do it all as one total problem. Or you can break it down like the book does into different steps, but you'll end up with the same answer regardless. Mostly your focus is going to be on getting this moles of sucrose. So what happens if you mix like two liquids together instead of a solid and a liquid? Well, in this case, what's going to happen is each of the two liquids will contribute to vapor pressure, right? Solids typically have a negligible vapor pressure, so looking at Raoult's law from the perspective of like the salt would not end up with an appreciable vapor pressure contributed by the salt the salt crystals themselves that you put in there. But if you mix two liquids together, as long as the two liquids are what they call here volatile, so that just means they have an appreciable, measurable vapor pressure at some given temperature, because some liquids will have an appreciable vapor pressure at one temperature but not at a different temperature, right? It's a temperature dependent thing. How volatileness increases as you approach the boiling point of the liquid. So when we say they're volatile, that means they have an appreciable vapor pressure at a given temperature. A and B, the sum of the vapor pressure contributions is some total vapor pressure plus the vapor pressure of A and equals the vapor pressure of A plus B. So how do I get this? Well, I'm going to have to rearrange Raoult's law, but now I'll have multiple terms because the overall vapor pressure is each of these two terms times their respective mole fractions. So the good news is most of these volatile liquids will not ionize, so we'll be able to just use the mole fraction straight up without any additional modification. So we can take this vapor pressure of A as a pure liquid times the mole fraction plus the vapor pressure of B as a pure liquid times its mole fraction. And keep in mind, this could be extended. So if you had a mixture of multiple liquids like 10, 5, 3, this just repeats itself. There'd be a C and a D and an E, and you just keep going. This can be extended to however many volatile components exist in this mixture. And as long as they behave Raoultian, this will work. This has deep applications in hydrocarbon separations, which they'll call cracking is the term that they use. So when they refine raw petroleum into its fractions, the fractions have names like kerosene and gasoline and other kinds of things. They're fractions they pull off. They're not pure substances, but the way they think of them is in a Raoultian kind of framework. They will come off based on their contributed vapor pressure to the combined liquid, and they'll use that to separate them into relative mass fractions that have different use cases. For example, as maybe an airplane fuel or a automobile fuel or different kinds of use cases for the different components. They'll separate these in the cracking process based on contributed mole fractions of each of the components, because the mixture in the gasoline is relatively Raoultian. So they say a mixture of two similar organic liquids, benzene and toluene. So benzene and toluene have very similar structures. We're not going to delve into them, but we're going to assume that this is essentially a Raoultian ideal mixture, that they are similar in structure. One just has this little thing over here, but they have the same basic part here in the middle. So they mix together nicely, and they're a Raoultian mixture. And so they'll separate. They said in a 1-to-1 mixture of the two where each mole fraction is 0.5, meaning it contributes 50% by moles to the overall mixture, then the vapor pressure of the solution is this, because it's half one plus half the other. Half this one plus half the other one. And then you sum those together to get the overall vapor pressure. So you can see how we can think about this mole fraction kind of like it's a percentage. I think that sometimes is assistive in our thinking. It's a percentage simplified. It's not it's like a 0.5, meaning like a 50%. You can think about it, it's 50% this and 50% this, but by moles, not by mass or volume, by the number of moles contributed. In this way, we can get a good estimate of the vapor pressure. Note that the vapor pressure of the mixture is intermediate between the vapor pressures of the two liquids. So they say here the total is intermediate between the two. As with non-volatile solutes, Raoult's law for a mixture of volatile liquids applies only to ideal solutions. So that means that the mixture has to be one where the two liquids are relatively similar in their constitution and in their intermolecular forces. If they're extremely different, it'll cause non-Raoultian behavior. Non-Raoultian behavior in liquids will form things they sometimes will call an azeotrope, where they cannot be separated anymore by a mixture due to the fact that sometimes the vapor pressure drops below that of either of the two constituents. So they don't separate on boiling anymore, and they just come off together because their intermolecular forces are tying them together and they're coming off as a set. So that's a behavior that's non-Raoultian. That's a behavior of non-ideal solutions. Some mixtures of volatile liquids, when in certain proportions, are non-Raoultian, and in other proportions are Raoultian. So that's another thing to keep in mind. The temperature matters as well. So most real solutions show behaviors that deviate slightly in a positive or negative way. And that's okay. Our estimate will still be good. As long as the deviation is reasonable, then our estimate is still good. And like I said, for hydrocarbons, we generally see that. For polar liquids in water, we generally see Raoultian behavior, but not all the time. I'm not going to delve into those exceptions, but just keep in mind they exist. Let's talk about boiling point elevation and freezing point depression. So because the vapor pressure goes down, the boiling point must go up because vapor pressure drives boiling point. So that relationships make sense. And we talked about how freezing point is the freezing process is interfered with by the existence of the solute. So they say the boiling point of a solution depends on the concentration of dissolved particles, just as vapor pressure does. Thus, a 1 mol solution of glucose in water boils at approximately 100.51 degrees Celsius at 1 atmosphere pressure, 0.51 degrees Celsius above normal. Now, the other thing to keep in mind that we're talking about is that the existence of this solute changes the boiling point. It's like an instantaneous measurement because as the water leaves, the concentration increases, right? So this behavior will increase, this deviation will increase up until some point. Glucose will also burn, so eventually it'll start breaking down into particles that fall out of solution, and there's other stuff that'll happen in real life. But keep in mind that as this boils and the water leaves, this concentration changes, and that can cause this deviation to also change. It's an instantaneous kind of measurement, right? And a 1 mol solution of sodium chloride in water boils at 101.02 because there are twice as many particles dissolved in this solution as there are in a glucose solution. So you can see here the deviation that's happening when you do this. And essentially what this does is extend our liquid range, right? We can be a liquid down lower and also a liquid up higher as well. So keep that point in mind. Again, I think it's best to describe this equation as kind of missing a variable here. There's an I that you can put in front of this molality here, a Van 't Hoff I, because remember that this molality will need to be multiplied by the number of ions produced, just like in the case of Raoult's law. So if you have a solute that breaks up into ions, you got to put the I Van 't Hoff factor. You could put it in front of the Kb, or you could put it next to the molality if you want to. If that helps remind you, because this molality is not a pure molality either. It has to be multiplied by I if this breaks apart into ions. So keep that in mind. Most textbooks will write it this way, and this is a standard way to write it. But keep in mind, I like to stick an I here in front to remind myself that if this breaks apart into ions, I need to include a Van 't Hoff factor. So Kb is the molal boiling point elevation constant of a given liquid. So the value of Kb changes with the solvent that you choose. So different solvents will have different Kb's, and they'll also have different Kf's, which is the amount of interference that the solute does to the freezing process, and the Kb is the amount of interference that the solute does to the boiling process by holding it together and elevating it. So these are both constants, but the form of this equation is actually the same. For freezing and boiling, the form is the same. Just remember that freezing points go down, so there's a negative sign there, and boiling points go up, so there's no negative sign there. As long as you can remember that, this equation is the same either way. You just got to get a different constant. You got to look up which constant you're using. Are we measuring boiling or freezing? Freezing point of a solution depends on the concentration of solute particles in the same way. A 1 mole solution of glucose freezes at negative 1.86 degrees Celsius, and a 1.0 mole solution of sodium chloride freezes at approximately negative 3.72 degrees Celsius. The change in freezing point is measured here, and again, you'll get the molality, and you'll need to put a Van 't Hoff constant in there if you have something that breaks apart into ions. It's a big reminder here. Again, they give us this form here where they stuck the I in there here at the bottom. I like to write this way to remind myself, but this is up to you. This is up to you. This is just the standard form you see in textbooks, but this is typically a more realistic way to remind yourself that you need that Van 't Hoff factor. You also need it in Raoult's law. Do not forget, because it can give you answers that vary dramatically from what the correct answer is as you're working on homework and test problems. I'm making a special note because it's very important. So using boiling point elevation to calculate the molality. So sometimes what they'll do is they'll boil something and use that to get the molality. So if they calculate the change in boiling point, so this is 101.27. So that means it was elevated by 1.27 degrees Celsius. Now, again, this is water, so we know the boiling point of water is 100 degrees Celsius. But if it was a different solvent, we'd have to look that up. And that's fine. The information would be given to you on an exam. I'm not expecting for you to memorize boiling points of liquids and freezing points other than water. So we can stick this in, we can rearrange it to solve for the molality. We can put in the change, which we calculate to be 1.27 degrees Celsius, and then use this to calculate the molality from the KB. They look it up in a table. Notice they tell you to look it up in a table. There may be tables in your homework or other resources that you'll need to check, because otherwise you are not expected to memorize these KBs and KFs too. You're not expected to memorize those. Those will be provided. So they plug those in and then they solve here, and they're able to get the molality as 2.5 molal. And again, a freezing point problem would work the same way. Just remember that the change is negative. You can solve it the same way, but don't tell me the freezing point became more positive, like that it was positive something. Make sure it's negative, because freezing points go down, freezing point is depressed, boiling point is elevated. Always remember that. That's how that works. Now let's talk a little bit about osmosis, right? So osmosis is the movement of solvent through some semi-permeable membrane. Most of the time when we have these membranes that they talk about, whether they're biological membranes or they are constructed membranes, these membranes often are permeable to solvent like water, but not permeable to ions or other molecules. You could make a membrane that is permeable to the molecules but not water. Such things exist. They'll often call these things reverse osmosis. When I have two solutions in contact with each other with some membrane in between, the solutions will try to equilibrate to reach the same concentration. So let's talk about this. If I have a solution on one side of a membrane that is like pure water with no ions in it, it's distilled water, and the other side has ions in it, the distilled water will try to rush into it to dilute the water. Since there's no possibility of equilibration, the water will all rush to dilute the other water. So that's an expected response. And it doesn't matter which way I construct the membrane, the overall result will be a more dilute solution, diluting the concentrated thing. So if I have a concentrated thing on one side and a more dilute thing on the other, water will flow to dilute the concentrated thing. And that's what will happen until we reach a point where it's the same on both sides, if that's possible. If you have a membrane where the ions can move but not the water, a so-called reverse osmosis membrane, then the ions will move to facilitate the same exchange. The result will be the same at the end. The system will try to reach the point where they are equal. Now, a lot of times they'll build this thing. They'll call this these bulbs, right? These bulbs they'll construct. And gravity is an important part of these bulbs, right? They'll put some more concentrated solution inside of some container and a less concentrated solution, and the more concentrated solution will flow up into it until gravity stops it, depending on how they build these things. And they'll measure that difference and they'll call it an osmotic pressure. Now that may seem really weird as a terminology until we get into the equation for osmotic pressure, which is going to be secretly the ideal gas law in disguise. We're going to see that in a little bit. But this is like a fake pressure. It's not like a pressure of a gas, but we can imagine it as like a strain on a membrane, because of the weight of something in both directions. They also think of it this way because when we think about like cells, a cell membrane can be destroyed by osmotic pressure, by the rapid influx of liquid in or the rapid influx of liquid out. Cells like to live in an area that has a similar osmolality or tonicity to what their internal components are kept at. They can maintain a certain homeostasis, a certain concentration on one side, and they expect a certain concentration outside their membranes. If you take the cells and you put them in distilled water, water rushes into them, flushes them, and kills them. If you put them in salt water, water rushes out of them and it shrivels them up and they die. So they want a certain tonicity, they want some ions, but not too much. They've adapted to living in freshwater or ocean water, and that's where they want to live, and that's the tonicity that their membranes are adapted to. And if they're taken out of that, they get killed by, they say they'll get killed by osmotic pressure, the flow of liquid in or across this membrane, which can be quite severe, and it can rip a membrane apart with the amount of particles that flow across it quickly. So they measure this, though, and we'll see how they calculate it in a little bit. This is the calculation for the so-called osmotic pressure, okay? Again, it's the pressure, we can say it's the pressure needed to achieve this equilibrium. Sometimes what they'll do is they'll apply a force to one side of the membrane. This is like a true way to measure this experimentally. They'll build this kind of U-shaped pipe and they'll apply a force to one side to keep osmosis from water from rushing from one side to the other. And the force they have to apply to keep that from happening is the osmotic pressure. Like it's a force over an area, it's a diameter if it's a tube, so they can measure it and call it a pressure, okay? So that's where this unit can kind of come from and where we can think about it. We can calculate this like it's the ideal gas law. In fact, we can use the ideal gas law. And this molarity here is moles over liters. It's actually moles over liters from the ideal gas law. This R is actually the ideal gas constant R, and in the same units as such, because osmotic pressure is usually calculated in atmospheres and temperatures in Kelvin. So this is pressure, P, equals molarity, which is really moles, divided by liters, RT. So if we remember the form of the ideal gas law, PV equals nRT, then this mole is just N over V. So this is nRT over V. So this is really just secretly the ideal gas law. Now, it doesn't really make a lot of sense, right? You'd say, how can this be the ideal gas law? This is describing liquid movement. How does this make sense to be a gas? Well, the way this works, and it's kind of like one of those backward things where like space is moving instead of the spaceship or something like that. This is something where we imagine that the solute particles are like the gas and the volume is created by the liquid. I know, that's the model by which this works. But somehow, it actually ends up working and giving a reasonable value. Like I said, the osmotic pressure of a 0.5 molar sodium chloride solution, again, against distilled water, is 7.3 atmospheres, a value that will support a difference in water level of approximately 250 feet. Water will rush in there to dilute these solutions. Okay, osmotic pressure can be very high. And this is what that pressure is. It's a force required to kind of prevent that equilibration from happening. And like I said, we can, normally solute concentration is given in molarity rather than molality because of this parameter like we said here. We don't have to express this in a temperature independent unit because osmotic pressure is already made at a specific temperature T that's in here, so they didn't need to use temperature independent unit. Also, this is much easier to calculate, and like I said, it's typically used for talking about a lot of biological systems. Red blood cells put into pure water, they break and they swell up like this and they die because osmotic pressure drives water into cells. We can think about it that way. But ultimately, it's a force of systems driving mixing and things wanting to become as low concentration as possible. Osmosis is still a colligative property. It favors the increase in entropy. Again, we could think about it as the increase in energy dispersal of the pure solvent as it passes through the membrane and mixes with the solution. We can explain osmosis at a molecular level, noting that molecules on the solvent side, because of their greater concentration, approach the membrane more frequently than molecules on the solution side. It's kind of like thinking about it like a vapor pressure. It's less likely for the solvent to pass through the membrane if there's solute in there too, because sometimes solute hits it and bounces off because it can't go through the membrane. Whereas on the pure side, it's constantly in contact with with just the solvent. So there's an overall net movement. These are all ways of rationalizing and thinking about the same thing, because this is a true physical force, and it doesn't matter how you construct the membrane, like I said, as long as all systems want to try to dilute themselves. So that's always going to be the outcome, regardless of how we have to rationalize it, right? They say the concentration of dissolved particles inside the red blood cells and surrounding plasma is approximately 0.3 molar, and the membrane surrounding it is semi-permeable. Semi-permeable, so it's permeable to water. What would the maximum osmotic pressure in atmospheres inside the cells be if the cell was removed and placed in pure water? So it's the pressure against pure water, and that's what we use this equation to calculate. So we calculate that as 7.3 atmospheres. In fact, red blood cells rupture if the pressure difference across the membrane is greater than 5. So the cells would burst if placed in water. And that is exactly what happens, because putting them in water is about 7.3. So again, this is a movement of water thing, and we can use this equation to calculate the osmotic pressure against pure water. If you put something else against it, it gets more complicated, and we're not going to calculate that here. Using osmotic pressure to calculate molarity. So if we measure the osmotic pressure, we can then use that to determine the molarity by rearranging the osmotic pressure equation, plugging in our osmotic pressure, plugging in our values. Remember that R is in the gas constant units here, not in joules per mole Kelvin or anything like that. You put in the temperature in Kelvin, calculate the value, and you end up getting 0.235 molar. Pretty simple here. Uses of colligative properties, right? They talk here about reverse osmosis. So sometimes you can power a system. Another way to do this is by putting pressure against it, right? So if you have one of these osmotic membranes, if you apply force to the solution side, you can push things through to the pure water side. That's a way that powered reverse osmosis can work. This is different from the reverse osmosis I was discussing before, where the solute particles can pass. Sometimes that's also called reverse osmosis. Again, the terminology is confusing. You can think of this as like a powered osmosis, a turned around osmosis, where we apply force to push solution particles through to the pure side where only the water can pass through. So we could purify seawater. The idea is I have the semi-permeable membrane and the solution on this side. I don't have any liquid on this side. I put force against it, pushes it through the membrane. It doesn't want to go that way. I have to apply an osmotic pressure exceeding the pressure in the reverse direction that would happen. This is very energy consumptive though, but it's used in desalination processes. So the seawater in, membrane, pure water out, they apply a force against it to push it through. Desalination, as an example, they say here a solution of this glucose will give an osmotic pressure, a value that can be read to 4 significant figures. The same solution, however, will only lower the freezing point by 0.04 degrees Celsius, value that can be read to only 1. Osmotic pressure can be used to find molecular weight or molar mass. These are same terminology. Remember that sometimes these books will use different terms for the same thing. They mean slightly different things, but for our purposes, we're really not going to worry about those internal distinctions. So they say they dissolved 20 milligrams of insulin in water and they diluted it to some volume. They get an osmotic pressure and they want to calculate the molecular weight. So what I'll do with this is I'll use this to calculate moles, right? If I can calculate the moles from the molarity, then I can take the moles and I can take the grams and divide them by moles and get a molar mass. So that's the trick here. So I'm going to use this to get the molarity, rearrange this to get the molarity, and then I'm going to use that molarity, multiply it by the volume that I was given, okay, the 5 milliliters that came from the problem to get the moles, and then I'm going to convert those moles into the molar mass using the grams also provided by the problem. 20 milligrams converted to grams. I divide that by the moles, and I end up with a molar mass. And it should be a really big number. Insulin's a really big and complex, proteinaceous complex thing, so it would have a really big molar mass. And that's okay if it has a really big molar mass. It's not a little tiny molecule. We talked a little bit about fractional distillation in some detail earlier, that this was a use for the Raoult's law equation, like separating benzene and toluene, right? And these big towers are used to fractionate petroleum. Sometimes they call this cracking, not fracking. They call this cracking. When you separate it with boiling and condensing cycles, they have these plates in them, and they're able to use this to separate it into fractions. And they show how this could work, right? If one of them has a much lower boiling point than the other, they'll talk about where boiling occurs, where p-benzene is and p-toluene is. and they can show that although the starting liquid mixture has a 1 molar composition, the composition of the vapor is not 1-to-1. Of this, for boiling, 71.3% is due to benzene and 28% is due to toluene. If we now condense the vapor, we can enrich it in one or the other. Boiling the new liquid mixture, we can continue to enrich this and put this through further boiling cycles to separate it. So if we volatilize a mixture, we can then condense that mixture and further refine that mixture from each step and just keep repeating that in order to separate it. So this is sometimes called a fractional distillation or a fractional boiling, and it works to separate compounds. As long as through the whole curve they stay Raoultian, it'll generally work. And so we can heat them up to the boiling point of the mixture, collect the vapor, then boil the vapor and further separate and refine this down until we've got it essentially separated and only have the more volatile component. But each time we separate off the less volatile component gets left behind. So we can use that to separate these mixtures. And like I said, that's typically how they refine petroleum, through a basic process like this. Correct. So they talk about the liquid vapor composition in this tie line and as they increase with further stepping. And you can also use this in a distillation column where you separate a mixture and the enriched receiver, and then you can do further boilings with further connections onto that. So one application of osmosis occurs in living beings in the kidneys, where part of how they separate out waste is through an osmotic type process. So this is why, someone who irresponsibly, through I guess it could be like some kind of frat party thing, if you drink a whole bunch of soy sauce or something like that. I mean, that's an example of where osmosis will kill you as liquid from your body flushes in to try to dilute this extremely salty solution that can cause, kidney failure and other kinds of, or multiple organ failure as water's drawn from one place to another. This is just a thought process you can think of, because from a simpler standpoint in the kidneys, part of what's going on is an osmotic process, right, where water's drawn in to dilute things in order to produce a waste, because these compounds can be toxic, and part of making them less toxic, which the body has to do to handle them, is diluting them to some certain extent. You can also do this dialysis, right? Both solvent and small solute particles can pass through these membranes, but large colloidal particles can't pass. This again is part of the process of purifying and simplifying out contaminants or poisons or something, or accumulated metabolic byproducts, to remove them from the body. This is part of what happens. This dialyzing is an osmotic related process. Not all membranes are only permeable to solvents. Some of them can be constructed that are permeable in other directions or against other things. Because they don't dialyze, proteins can be separated from small ions and molecules, making this a valuable procedure for purification of proteins, but also part of how the kidneys work to pull out these small molecules and liquids to one side and these other materials to the other side. Hemodialysis is used to clean blood. This is a function, again, that goes on liver and kidneys together to do this, to clean out broken blood cells and to clean out poisons and toxins and other things that can accumulate in the blood that then can be passed into urine. Small waste products pass through the dialysis membrane from the blood to the solution side where they are washed away, but cells, proteins, and other important blood components are prevented from their size from passing through. And they have to do this process. They also talk about being an organ donor. This is actually a really valuable thing. People who could become seriously injured or have autoimmune reactions or other kinds of processes may need organs in order to survive. So it's actually a really good thing to do, because if something happens to you, like you end up in some sort of accident where some of your organs are still in a viable state, this can save lives and really help people. I like this note in the book because I've known people where this would be a really benefit if there were more organ donors available. So, all right. So this is the end of Chapter 11 on solutions and their properties. I hope you found this very edifying, and I will see you all in the next one. Thank you.